In this lecture, we'll talk about method of lines, MOL, and stability. For schemes, for the heat equation that we talked about in the last video. Alright, so the method of lines means that in order to solve the equation ut is equal to uxx, u is a function of x and t, right? So the idea is that we do it one by one, we divide and conquer. So we discretize, if you discretize space only, which is so-called semi-discretized. So like what we did last time is fully discretized. We discretize space and discretize time. We come up with a grid along x and a grid along y. And so if you discretize space only, then add, which means add some fixed grid point xi, okay, xi. What is our function u? U xt becomes u of xit, right? And xi is fixed. So this is we're going to call this becomes the function of t. So we call that u sub I of t. So schematically, this is you have the x domain, which again we discretize it: x0, x1, x2, xm plus 1, right? And along every point, you have a half line that shoots above from xi, right? We're going to call this guy, there's a function along this line, u0t, okay, u0t, because your x value is fixed at x sub 0. So we have a function of two variables. Is one variable is fixed, it becomes a single variable function of the other variable. And here is u1t, and so on and so forth, right? So here is u sub mt, here is u sub m plus 1t, okay? So then the equation is ut is uxx. This is that you have an unknown function u if you take the partial derivative with t, right? So this becomes still a function of x and t, right? Once after you take the partial derivative, you still have a function of xt, and it says these two functions are the same, right? U sub xx is also a function of x and t. So in particular, we have that, well, if you fix the x value at xi, you also have u sub t at xi t is equal to uxx at xit. Alright? So what that means is that, well, we know u at xit, we call that u sub it. So we u sub it, now before it was a bivariate function, now it's a single variate function. We can call that prime, okay? What's left is what we deal with uxx, alright? So uxx at xi, that's a approximation to uxx at xi. which we know. So that's the u at xi plus 1 minus 2uxi and plus ui minus 1, right? And by our new notation, we're going to call that u sub I plus 1t minus 2 uit plus ui minus 1t. This is divided by h squared. Of course, we still have the boundary condition, which give us that u sub 0t is, using our notation of the last lecture, is g sub 0t, and our last one, um plus 1t, is simply that g1t, the boundary condition, okay? So we basically turn this equation into this partial differential equation into ordinary differential equation, PD to ODE. If we rewrite this, if we call this ODE system, basically, if we call this capital U, we're going to have U sub 1t, all those unknown t-dependent function. We put them together. It's this guy, okay, this guy. Then we have this ui prime t, right? This is ui plus 1t minus 2 ui t. I'm rewriting what we had above, plus ui minus 1t is divided by h squared, and this I runs from 1 to m, right? So we have m equations. We can write that as a linear algebra system. Okay. So we have this ut is equal to 1 over h squared. All right. It's a similar procedure as we did before. So we're going to get this negative 2, 1, 1, and then 1, negative 2, 1. Here you have 1, so forth. This times u plus, remember, maybe let me write a little bit more detail. So this u is a vector functions, okay? U1, if the U1 prime t is equal to U2t minus 2U1t plus U0t, right? Divided by h squared, okay? So this negative 2 is a negative 2. This 1 here is this 1, right? Because that negative 2 will hit the U1. So this is like, you have negative 2, 1, all right, 0, 0, 0. We'll multiply with my U1 t all the way to umt, right? You still, we have this 1 over h squared. You still have plus, this take care of u2 and u1, you still have the u0 t over h squared, which means we're adding 1 over h squared. We know u0t is g0t, right? This given boundary condition, and this is not happening for when I is 2 to all the way to a minus 1. So you're going to get 0, 0, and finally it will happen again at the last node. Okay. So here u is a function of t only, so it's u sub t is just u prime. So we're going to get a system of the form u prime is equal to au plus a function t. All right. This is basically a coupled ODE system, right? A coupled ODE system. So that means, implementation-wise, we can use the ODE solvers, or maybe some ODE existing packages to solve. Those are what we covered in 361. The ODE solvers. For example, we could use the forward Euler, FE. What that means is that if we use a U vector to denote the numerical approximation to the capital U, then we have this vector at n+1 time step is equal to the vector at n time step plus delta t times all this right hand side, right? This AU plus G, that was our F. So this is like the F of U, right? F of U. So this is delta t times that F of U at time level n. What is that? That is just un plus delta t times that whole AUN plus G at Tn, right? G at Tn. Remember, we have this is our G of Tn. This is the GT, and that matrix is our A. Okay. So for the stability analysis, as we did at the time, so what we have is that, well, if A I have eigenvalues lambda 1 to lambda m, those are A's eigenvalues, right? So what we need is that this delta t times lambda I, those are in the stability region of the solver, right? Of the solver, which, if you recall, for forward Euler, that region is this circle, right? This circle. We can do a better job plotting that. So here is -2. That's a stability region for forward Euler. Let's take a look at why that's still true. That's the same as we concluded before. So if we look at the simple case of when G is 0, so we have zero boundary condition. What we have is then this U vector n+1 is equal to U vector n plus delta t times that A U vector n. Alright, so this can be, of course, rewritten as identity plus delta t A U vector n, right? So if we start from U0 and we go from U1, from U2, so we now are going back, we have this UN+1, we go from UN+1 to UN formulation wise, and then UN is the same vector, so it's I plus delta TA. UN, you apply the same formula, UN is I plus delta TA, UN minus 1, and so on and so forth. in the end, we know it's I plus delta Ta to some power of U0. What is that power? The trick, as we did many times, is that when the index for U vector decrease by 1, the power exponent of I plus delta T increase by 1. So the sum keeps the same, right? The sum is m plus 1. So now the index for U vector is 0, so here must be m plus 1. When we assume the eigenvalues of A's are lambda 1 all the way to lambda n, let's say, for lambda I its eigenvector is vi, so we have A vi is lambda I vi, okay? Here vi is a vector, so this, if we write all of them together, you're going to get A v1, v2, all the way to vm, okay? And this is equal to this can be written as lambda 1 lambda n times v1 v2 vm. Alright, so we are rewriting this guy. Now here I is from 1 to n as this guy, right? The equivalent. You need to do this by hand and stare at this for a few minutes. This is simple linear algebra stuff to rewrite a bunch of equations. Here a bunch of matrix vector equation into a matrix equation. Usually we rewrite a bunch of scalar equations into a matrix vector. Here we rewrite a matrix vector, a whole bunch of matrix vector into a matrix. Okay. So we're going to call this guy S. Okay, this guy S. And also this is of course also S. So each little v is a vector. So put all of them together is a matrix. And we're going to call this diagonal matrix a capital lambda. So what we have is that we have AS is lambda S, right? Which is to say A is when S is invertible, we have A is S. Well, I made a mistake above, so this should be this way. That's a lambda. So it could be tricky. So here what we have is that this is S lambda, right? So A can be written as S lambda S inverse, right? Assuming S is invertible. In this case, A is called diagonalizable. Alright? In this setting, what we have is that we have this U. We have the I plus delta Ta. What is I plus delta Ta? I can be written as S times S inverse plus delta T is a scalar times our A is S lambda S inverse, right? Delta T is simply a scalar, so this is S times S inverse plus S times we have our delta T lambda, so this delta T lambda 1 all the way to delta t lambda m, right, as inverse. So what is that? That's just s times, you have a 1 from the first term, so it's 1 plus delta t lambda 1, 1 plus delta t lambda m, this whole thing times s inverse, alright, s inverse. This gives us a way to compute the I plus delta ta, the whole thing to the m plus 1's power. Okay, if you look at what's going on, so you're going to get I plus delta ta times another I plus delta ta times, you're going to get m plus 1 of them. Alright, m plus 1 of them. So this is going to be this s times that 1 plus delta t lambda 1, 1 plus delta t lambda m. That's my first guy, first I plus delta ta. Then I have my second guy, which is s, 1 plus delta t lambda 1, 1 plus delta t lambda m. This is s minus 1. And then another s, and so on and so forth. Alright, in the very end, you're going to get a matrix, and then you have s minus 1. So you see that this s minus 1 and s, they cancel each other. All these intermediate guys are canceling because it's s inverse times s, it's identity. So we have one s left, another s minus 1 left in the very end. Okay, in the middle, what's left is a product of diagonal matrices. A product of two diagonal matrices is still a diagonal matrix. So the product of all these diagonal matrices is a single diagonal matrix, with each entry being this diagonal entry to the m plus 1's power. You get m plus 1 of them. Lambda m to the m plus 1's power. Okay. So we recovered what we did before. So in order for this 1 plus delta t, in order for this matrix times u0 to not blow up, you want this plus 1 plus delta t lambda I, the module is less than 1. Alright, it's less than 1. Because you still get this guy to the m plus 1's power. And that's when we concluded this delta t lambda I, remember, is you treat that as a complex number. The lambda I can be potentially complex, and this is basically the distance between 1 plus 0 I, right, and negative 1 plus 0 I and delta t lambda I, right? When you calculate the distance, you subtract them. So it's delta t lambda I minus 1 plus 0 I. If we go back to our notes, that's of course 1 plus delta t lambda I. So between becomes the distance. So you have the distance, that's our negative 1, 0, right? You have the region being whatever is all the points that is less than distance 1 away. That's a circle. Okay? All the points on the complex plane that whose distance to this point is less than 1. That's exactly the definition of this disk. Now for this matrix A, we did that when we studied the steady state elliptic equation in the first part of this 362. We know this is negative 2 -2, 1, 1, 1, 1, right? This matrix. We studied this eigenvalue. We showed that the lambda I is equal to 2 cosine, if you go back a few videos, I pi h minus 2 divided by h squared. So if you look at lambda 1, which is 2 cosine pi h minus 2 over h squared, right? Now when h is tiny, pi h, cosine pi h, cosine x can be approximated by 1 minus pi h squared over 2 minus 2 divided by h squared. Again, let me write that down. So the reason we have this is because cosine x is like 1 minus x squared over 2 for small x. That's Taylor expansion, right? You do Taylor expansion for cosine x, you get the first two terms, which is 1 minus x squared over 2. So if you simplify this, you get this is minus pi squared. Okay. For lambda m, so this for the last one, you're going to get 2 cosine, your I is m times pi. What is our h? H is 1 over m plus 1, right? And we have m plus 1 intervals. Minus 2 divided by h squared. So this is approximately, the reason is m divided by m plus 1 is almost 1 when m is large. Okay, so this is approximately 2 cosine pi minus 2 divided by h squared. We know cosine pi is -1, so that's -4 divided by h squared. Okay, so this lambda is getting smaller and smaller from lambda 1 to lambda m. When h is small, 4 over h squared is large. So this means that we need because when we did that diagonalization analysis, we have this. We need the 1 plus delta t lambda I. We need this less than 1 for all I, right? For all I. Because all these are negative numbers, all right? So we need the delta t lambda to be on we need the delta t lambda to be here, right? Those are your delta t lambdas. Delta t lambdas. Lambda is negative. Delta t lambda is also a negative number. So this, because the absolute value of lambda m is the largest, so we only need is enough. It's not only is enough to ask 1 plus delta t lambda m to be less than 1. Alright? In other words, we ask delta t lambda m to be, this is all we know is negative, and this is larger than -2, right? That's here, -2. Which is negative delta t times 4 of h squared. This is larger than -2, so we have delta t is less than 1/2 h squared. That's a condition for you to use the fourth scheme of the last video, the forward Euler in time, and standard central in space. for solving the heat equation. That's the condition for the size of delta T. So we need, once you decide spatial discretization, you have the size of H. We need a delta T that satisfies this condition for the first scheme for ut is equal to uxx to be stable. Right? What is the first scheme? Again, let's just ui, what we did last time, ui n plus 1 minus ui n divided by delta t. This is equal to h squared ui plus 1n minus 2 ui n plus ui minus 1n. Alright? So now for the second scheme, which is a Crank-Nicholson, this becomes the delta t lambda I for in that case, we just change the ODE solver basically. Everything else stays the same. We have a new stability region because we have a new ODE solver. This stability region now becomes because the Crank-Nicholson scheme is unconditionally stable, as long as we need the delta t lambda I to be in the left half of the plane. But we know that lambda I is negative, so it's always in the left half of the plane. So this is the second scheme. That's why it's called unconditionally stable. Alright, but no matter what delta t you choose, delta t lambda I is always in the stability region. No matter how large delta t is, delta t lambda I is always in the stability region. Okay.